So our second talk is about CRDTs. Parallelism is just really hard. And there's this whole family of things called CRDTs that give you a sort of uniform approach to parallelism for a wide, not everything, but a wide range of things. So I always think, oh, I want to understand more about CRDTs. And one of the important things in computing is to relate different approaches, right? So, what's the most important thing about Turing machines? That they have exactly the same computability power as lambda calculus. So there's two standard approaches to CRDTs, and this is going to tell us something about the equivalence between them that's well known, but making it formal and something that you can actually prove and use. So I'm very keen to hear about this.
Hello. So hi, everyone. I'm Nathan Liittschwager. I'm a PhD student at University of California, Santa Cruz. My advisor is Lindsey Kuper. So like was just said, I'm going to be talking about CRDTs, conflict-free replicated data types. So I'll begin with some background. If we have a, say, web service or some kind of service, and we want it to be more available or more fault tolerant, we would replicate this service across different nodes on a distributed system. We can represent this service usually as like a state machine, which is what our perspective in the paper. So here is just replicas 1, 2, and 3 at US West, US East, and Oceania, for example. Okay, so a nice way of doing replication is with these conflict-free replicated data types, and there are largely two flavors. There are the op-based CRDTs, which they enforce consistency among the nodes, meaning they all have the same sort of results to queries. They enforce consistency by ordering the updates between them. So when a replica has an update, it will then propagate that update to the other replicas, and there's a partial order, usually called a causal order, that says these updates need to be applied in this order. So roughly each replica is executing the same updates in the same partial order. The concurrent updates are allowed to commute. So the other flavor are the state-based CRDTs, which they enforce consistency by requiring that the state space is a joined semilattice. And then they propagate their states to the other replicas. And since it's a joined semilattice, as long as they can perform a merge, if all the replicas can mutually merge with each other, they will eventually converge and give the same state. Here's just like a little example. So on the left here, we have the op-based CRDT. The example, by the way, is a grow-only counter. So our state space is just the integers. So on the left, we have an update, increment 5, at replica 1. It propagates that update to the other two replicas. And then replica 2 increments by 7, and then also propagates those. Those updates get executed. And then at the end, we have that each replica has a state of 12. On the right, we're also doing a grow-only counter, but now we're taking a max as a way to do the merge. And when you are taking a max between 5 and 7, obviously 7 is the larger number, so we end up with a final state of 7 at each replica. So even though these are both sort of implementing the same data type, and they have the same client-supplied updates of increment 5 and then increment 7, we can end up with different states. It was this sort of example that we first noticed that maybe there's some nuance to the way that they are equivalent. So we thought, like, OK, in what sense are these CRDTs actually equivalent? We know that from prior work, Shapiro et al. In 2011, that there are translations to transform an op-based CRDT into a state-based CRDT, and then a state-based CRDT into an op-based CRDT. Of note is that these translations are not inverses. So if you go from the left side to the right side and then back to the left, you don't get back the same CRDT. It's actually something different. What Shapiro showed in his paper were that these translations preserve strong eventual consistency. So if you take your original CRDT, translate it into the other kind, then the result still exhibits strong eventual consistency, meaning that when updates at replicas cease, and then the replicas are allowed to communicate with each other, they will eventually converge to the same state. But we were kind of curious about sort of non-converged behavior, because in a lot of distributed systems, you don't actually stop local updates, right? Like you allow clients to be always providing updates. Oh, right, and then one other thing that I wanted to point out is just that strong eventual consistency is perhaps not quite enough, because a mapping which would also preserve strong eventual consistency would be a trivial mapping that takes a CRDT and then maps it to a data type with one state and updates do nothing. That's converged just immediately. So somehow preserving strong eventual consistency may not quite be enough. So even though we have these questions, we saw in the literature that sometimes there are assumptions that one can focus on one type of CRDT and sort of ignore the other because we have a translation between them, and it's taken to be equivalent. So in some sense, we saw that this claim of equivalence to be load-bearing, even though we're sort of interested in, as programming language people, what observational equivalence really means with respect to these data types. So what do we mean by the same? If we have op-based CRDTs and state-based CRDTs, what is the real sense that they are the same? So we have here sort of these computational trees. On the left, we have an op-based CRDT. On the right, we have a state-based CRDT, and then the initial state and a path down to a converged state. The intermediate paths here are possible computations that could happen. So it seems obvious from Shapiro's work that there should be some kind of simulation between the initial states, where all the CRDTs have all the replicas have the same state, and the converged states, where again all the replicas have the same state. But what we were interested in are whether we could put these intermediate states inside a simulation as well. So our first major contribution with this paper was showing that, in fact, you can. If you take a given CRDT and then translate it, you can construct a simulation, two simulations actually, from the original to the new CRDT, and then the other simulation from the translated CRDT back to the original. We proved that you can construct these simulations. The main focus of the paper, we do have in the appendix both translations, but the main focus in the main paper is the translation from op-based CRDTs to state-based CRDTs, because we found that to be the more interesting case. Our second contribution was leveraging the first one. So once we know that we have these simulations, we were able to define this sort of simple imperative language, which allows a programmer to interact with CRDTs through while loops, updates, and queries, and then show, there's also a variable store, and then show that if we have a program P running with CRDT A and that program terminates, then if we translate CRDT A to CRDT B, that program will still terminate. And then this also goes in the other direction. So it's actually a co-termination result, meaning that we can't actually construct a program to differentiate the original CRDT or the translated version. So in that sense, they are equivalent. What I wanted to talk about, though, for this paper was really the simulation proof, kind of the key idea how we wrote the proof, because it's largely, our second contribution relies on that simulation existing. So that's what I wanted to talk about here. So let's take a closer look at the translation. We're focusing on the translation from the left to the right, so the G. Given an op-based CRDT, it's mostly defined by these two functions, prepare and effect. So prepare takes an operation and the current state, and then it generates a message which contains the effects of that operation. And then there's the effect function, which takes the current state and a message, executes that message, and then updates the state. Local updates are defined as a composition of prepare and effect. So when a client does a local update, prepare happens, immediately effect happens, and then the message is sent off. And then the other replicas will use effect. The state-based CRDT is mostly defined in terms of the joint semilattice and merge. So the normal translation that you would use here is, for the state-based CRDT, we would represent the state as sets of messages. When we do a local update, we delegate to the underlying op-based CRDT to generate a message and then add that message to the set. We made a slight change from Shapiro's algorithm. So Shapiro gave an algorithm from op-based to state-based and then one from state-based to op-based. We made a small change where we interpret the sets of messages into states kind of on the fly. This is not a very, oops. There we go. This is not a very efficient way of doing this translation, but it's nice to work with theoretically. So the basic idea is if you have a set of messages that are partially ordered, you can then partition that set into sort of grades, where in each part of that partition, all the messages within are concurrent. And then we can just take any message from that grade and then apply it. And so this lets us define this interpretation function recursively. So just to say again, we're being given an op-based CRDT, translating it to a state-based CRDT by representing the state as sets of messages. And the only thing we need to remember was the initial state. And we just translate to the current state by applying all those messages. And the definition of simulation that we use is the somewhat standard one. So we're focusing on this talk just the simulation with a given op-based and then the translated state-based. We allow one CRDT to take a step where that step is defined as either an update, a delivery, or a query. And then we construct a matching set of steps on the other CRDT. Technically, we're using a weak simulation in the paper, but just for this, we're not going to get into the exact details. Much more of a high-level take here. So when we were constructing this simulation, we came across an example like this that sort of shows the simulation is sensitive somehow to the network semantics of our CRDT. And this is really what led us to the question, what is the sense that these two kinds of CRDTs are equivalent? So at the top, if we were to have an op-based CRDT doing an increment 5, broadcasting that update, then in increment 7, broadcasting that update, then the other replicas have two possible messages that they can deliver. They can deliver an increment 5, and then they deliver an increment 7. It has to be in that order due to the causal ordering, the partial ordering on these messages. But in the state-based representation, we need to be a little careful about how we send state to the other replicas. So for example, if we do increment 5, then increment 7, we can end up with this state that contains two messages. If we then broadcast that, the other replicas can only merge that state, which contains both messages. If we then interpret that into the op-based state, then we somehow jump ahead, right? A replica on the op-based side could show a state of 5, but a replica on the state-based side would only show 12 or more. So in some sense, we have to be a little bit careful about how the communication between replicas works. OK, so I'm going to show the two sort of main steps in the simulation. So we're going to first look at the op-based CRDT simulating the state-based one. So given this op-based CRDT, we construct the state-based version of it, representation of it. And we'll say that H and S are in simulation if we can interpret H into S. There's some side conditions, but for the purpose of this talk, we won't get into that. The critical step for this is how we simulate merge. So if the state-based CRDT performs a merge of a set of messages, we need to simulate that on the op-based side. This is weak simulation, so we're allowing multiple steps. More or less, we're going to be picking out the messages in that set and then delivering them one at a time. It's a fairly straightforward argument. The somewhat more interesting direction of the simulation is showing how the state-based CRDT simulates the op-based one. And again, we're looking at how delivery of messages works. So suppose the op-based CRDT delivers a single message, M. The state-based CRDT can only merge a set of messages. So we need to simulate the delivery of one message by merging a set of messages. And we need to be careful to not overstep somehow. The way that we sort of think about this is whatever H chooses to merge, whatever that replica chooses to merge, we want its state H to somehow already know about messages 1 through mk minus 1, where the m sub k message is the one that contains the effects we care about. The way that we do this is we sort of restrict the state-based CRDT to always broadcast just as frequently as the op-based CRDT. So by constantly broadcasting just whenever the op-based CRDT does, we will guarantee that replicas have access to a number of states, and then each of those states is sort of growing by one message at a time. So then if we look at a replica, and that replica wants to deliver messages M1 through M3, for example, M1, M2, M3. Remember that these are ordered by causality. In practice, we would use something like a vector clock. The order that has to be followed is you first deliver M1, then you deliver M2, and then finally you deliver M3 in this example. On the state-based side, we would simulate by merging the set that contains M1, then the set that contains M1 and M2, and then the set that contains M1, M2, and M3. And so at each simulating step here, the replica, the state-based replica, knows about the messages that happened before the message we currently care about merging. So with M1 as the first message, there's nothing to know. With M2, that replica already knows M1, so when we merge the set M1, M2, the only observable change comes from M2, and so on. And that's essentially the heart of that proof, is by checking the existence of these sets, making sure that they're available, which they are because we're forcing broadcast to happen very frequently. So that's more or less the heart of our proof. And much of the other contributions in our paper relies on those simulations. So our conclusion here is that the observational equivalents of CRDTs are somehow sensitive to the network semantics. So if you want to say that a CRDT is equivalent and we can ignore the other type of CRDT, then you need to somehow consider the network semantics involved and make sure that broadcast is happening just as frequently or something similar. Nonetheless, if you know that the communication semantics in both kinds are roughly the same, broadcasting just as frequently, then you do have an observational equivalence in a formal sense. And because we have a pair of simulations, we actually obtain a trace equivalence, where we're looking at traces of updates and queries and the values returned by those queries. So if you have a safety property defined on a trace, then that safety property really will transfer via the translation, the CRDT translation, because we have that trace equivalence. And then also we have our co-termination result, which was not the focus of this talk, so if you want to see the details, you can check out our paper. And yeah, that's what I wanted to talk about today. Thank you.
First question.
Hi, I'm May Milano, Princeton. I am curious to know if you also have sort of the equivalent negative result, which is that there is no possible encoding of op into state or state into op, such that you could get simulations without being sensitive to the network semantics, as in the network semantics simply must matter.
Oh, that's good. I guess we do not have the equivalent, the negative result as you just said, but I see no reason why we couldn't leverage the same techniques we used here to construct it.
negative result would actually be true, that the network semantics are fundamentally important.
We definitely believe that they're fundamentally important, so let's talk.
Okay.
Thank you.
Hello, Henning Obert, VW Erlangen. You told me earlier that you, in the end, decided against a co-algebraic approach.
Yes.
But could you do it? So is there still a functor in the lifting that makes your simulations co-algebraic simulations?
So could we do it with co-algebraic simulations?
Yeah, exactly.
I think so, because we don't show it here in the talk, but in the paper we have a semantics for the network, which you can define as a co-algebra pretty easily. It would be like a step into the power set of the states. You could use like the saturation definition of co-algebraic simulation. You could obtain it that way. Yeah.
Okay, nice. Thank you.
Thank you. Nice question.
Hi, thanks for the talk. I was wondering if you had, maybe I missed it, or if you thought about like a sort of result along the lines of the network semantics matters, but if you allow arbitrary merging rather than sort of the ordered merging, you used to get like a soundness or something where it's like you're at least like you're reducing the space of behaviors you see.
So I haven't thought of doing it like that, but I think there might be a way. I think maybe I might need to ask some clarifying questions. So if you want, we could talk a little more.
Sure. I did have one more question if there's a moment. It seems like what possible use for this would be like compiling things. Like if you can sort of specify whichever kind you want and then use this to translate into like the appropriate runtime version. Have you thought about like the performance if you were going to do something like that?
So strictly speaking, no, we didn't think too hard about the performance because we wanted something that was sort of nice to work with theoretically, even if it would be inefficient. There is a more efficient way of doing that translation, which it is actually more or less what Mark Shapiro did in his paper. There's just like a slight, it's just slightly more difficult to work with. But for compilation, I think it would be hard because if you're going to represent states as sets of messages, then that state is going to blow up over time. So you would need some way to forget the past messages and shrink the states. But there might be a way. Yeah.
Thanks.
So I see somebody queued up behind you who hasn't asked a question before. Did you want to ask a question?
Hey, so thanks a lot for the talk, and I enjoyed it. I guess so the two translation functions that you had, you named them very suggestively as G and F. So are they in fact adjoints? And I guess the other question was, if there is an adjunction, do you also have like another adjunction? Like, do you have a triple or what's the?
Can I change your question to, is there an adjunction? Because you didn't say that.
So I probably don't know enough category theory to really answer that question. Certainly it's been pointed out before that it looks like an adjunction. So there might be, if you know enough category theory, maybe we can figure it out.
Okay.